Welcome everybody to another Discus tutorial. Today we're going to talk about macros in Discus. This tutorial will pretty much continue from the last tutorial where you've seen what Discus is able to do in general. Today we are going to talk about how you can actually achieve those ideas in Discus. Therefore I've created a few macros. We'll talk about two macros today. The first example will be just one simulate cell macro, where we can connect a few other macros into this envelope macro with the add command. So you can also start macros in general with the add and then the name of the macro command in the command line of the Discus suite, for example. So we are going to see that. We need to preliminarily define variables and look for an input structure, and then we can use the macro to simulate structures, bigger structures, for example, more complicated structures, powder patterns, PDF patterns, and so on. And later on we will look at those results in qplot. The second example we'll look at will be the refinement macro. It will be a full refinement macro set, which you can start with the refine.mac macro, either in an interactive mode, or we'll learn how to use it in a parallel mode, which uses all cores of your computer with either the MPI-exec on Linux or the parallel command on Windows. Therefore we'll use the zinc selenide nanoparticle refinement from the workshop, which looks like that. So it's a set of macros and a few folders, and it looks quite complicated maybe on the first glance, but there are just a few main macros you really need to change when you want to change your structure, your model, and refine it against the dataset. So we'll look at all those folders and macros. So at first, the folders. We will mainly use two folders, the cell and the data folder. So the cell folder is used for putting your input structure in there, or input structures, and the data folder will contain your data set against which you want to refine your model. Of course there are several other folders like the diff final, indi, and so on. Those are folders which will store parameters and fits created during the refinement, and they will be used as an analytical tool mainly. For example, the temp folder will contain the output of the diff_best macro, which is quite useful for looking at your best fit of your current refinement. Of course we need to learn how the macros are built up in general. So at first there are several macros where you need to define variables, where you need to define your input files, your input structure, and of course your refinement parameters, which is stacking fault probability, the size of the particles, and so on. So that's the first step you need to do. Then you can start the refine.mac, which is the main macro. It will trigger all the other macros in the folder, and also the discus.zinc selenide macro, which is the main macro which will cover the shape of the particles, the porosity or surface modifications you want to insert here. And there are a few macros in the folder which just deal with the analysis of the data. You theoretically could delete them and it wouldn't change the outcome of the refinement, but it's actually useful to have them concerted in a folder. There are of course additional macros which are also not used for just the refinement. That's for example the refine underline continue mac. This macro is used when your refinement comes to an end at some point and you want to continue the refinement because your parameters haven't converged yet. Then you should start that refinement command. Also there's the diff_best command, which is an assembly of all best parameters found during a refinement, and from that you can create your best fitting structure or powder pattern, whatever you wanted to create. Of course, there are also again those other cuplot macros which you should individually start after a refinement. Okay, we will jump right into the macro, which is here the simulate cell.mac in our first example. The whole folder is dedicated to this macro, and this macro will look like that here. So when you start it with the add command in the Discus suite, it will go to the Discus program and start another macro, which is the variable mac. We can look at that one here. It defines variables, and later on some values will be allocated to use those variables. And then here's the first $1. So $1 will be a variable you have to find it in your own command line. So it's standing here for the cell file, so for the structure file we want to read and use for the model. So when we go to cell, we can, for example, look at the zinc selenide cell file here. So it contains atoms. It's pretty much an atom list. You can create it out of a zip file or something like that, and then you obtain the cell file, or you can write it yourself. And in this command, this is going to read this cell. You have to give it a name with the $1, and you have to give it a name with the second parameter, $2, manually, which will be the diameter of the particle you want to calculate in our case. After that, it calculates the cell dimensions for this diameter, and then it rereads the cell with the right diameter, cuts a sphere out of the block of those atoms, and then starts with the next macro, which is the plot cif macro, and it pretty much just plots or writes a cif file into the result cif folder, which is here. After that, the main macro is going to start the powder and the PDF macro. So the powder macro creates your powder pattern out of the model, so out of the structure file, and equally the PDF macro, the last macro in this series, is creating the PDF, again with the variables we have defined before. In an exact mode, what everything else will mean can you look for in detail in the manual. What else is in here? Then we have the simulate cell macro, which is just a copy of the simulate cell. So what it does, it uses those lines, the cif lines, to read a cif file instead of a cell file. So we can see later on what this macro does then, and then there's a series mark what you can write to, for example, simulate a lot of structures once your macro is correct. And those are the input parameters you have already seen here, the $1 and the $2, for example. So let's run one of those macros. Let's do the simulate cell. So you go to Discus, you go to the path with the cd command, and then you start with the add command, the simulate cell macro. And again, you need to define the $1. So we want to, let's say, we simulate a zinc selenide structure. So I have to type the name and then the size of the structure. Let's make a ball, a sphere with 25 angstrom in diameter. It calculates that, and again now in the PDF folder there will be a PDF created of the zinc selenide. Here again in the powder folder there's a powder file created, and in the cif folder there's a cif file created of the sphere we have created, which looks like this at the very end. Again, equally you can reread these cif files and just calculate a powder out of that, or we'll do it with the scope crystal cif, for example, here, which looks like that. So what we can do is we take the same macro, but use a sieve here, and then how it's called co-crystal. Then we're going to calculate maybe a bigger co-crystal ball of 45 angstrom. Okay, that will take a while because we are in exact mode and we don't have periodic boundaries here. Okay, so what we can look at now, we can look at, for example, the powder data. When we go now to the cuplot and run the fancy 3D macro, plot macro I wrote a few weeks ago, so you can just look into those files. Pretty much calculated 6 patterns and shifted them a bit so we can easily see what we created here with other files. Reading the plot again. So here you see the powder pendants created from, for example, the zinc selenide structure. It was this one, so it was just a 25 angstrom spherical particle, so just 2 nanometers, so very broad reflections. When you see the black peaks here of kaolinite, for example, where I have calculated a really big crystallite, so you can sharp peaks in the powder pattern. Equally, you can do that for the PDFs. Let's go to the PDF folder and run another macro here. Again, 6 files, and we'll see the PDFs of those structures in the folder. Again, this was our zinc selenide. When we go now back to the suite, for example, while we open a new suite, just for trying that. What is this? Amazing. Let's do it here. Okay, the other one finished, but anyway, I have opened that one now. And when we go back to the macro, oh my gosh, here it is, and run the simulate cell of the zinc selenide, underline, what was the name? Word side, right. Word side, and do a smaller particle, an even smaller particle, and we rerun that macro again. You will see that the signal is reduced here in the higher range, R range. So when we scroll it to like 20, I don't know, we calculated it to 40, and then you see we don't have any signal here because the particle is really, really small in that case. Okay, that's pretty much how you create powder patterns or other patterns or structures. With such a simple macro, we can just look at the sieve of our co-crystal. For example, say the co-crystal is here in red, so it's quite a big particle crystallite we have created here, and again here the particle is quite huge out of caffeine and the naphthoic acid. Okay, that was our simple example. We probably should mention that we are able to look at those single, let's go to powders, single patterns also. So when you do a reset here and just want to look at the co-crystal, for example, you can plot it like that in qplot, and then you just see the powder pattern of the co-crystal or PDF or whatever you want to look at. Okay, then we go on with the second example. Alright, let's head into the next macro, which is the full refinement macro of zinc selenide. This macro is also taken from the workshop, and you can start this macro with the refine.mac command. Okay, this will execute all the macros below this main macro, so when you want to look at it, It contains a lot of macros. It actually does at the moment 5 cycles of refinement, so 5 generations, and thus 5 loops over the macro set, so not a lot, just a quick refinement against the data. And then you obtain a diff_best file, and this contains the final results of your refinement. So here you refine, for example, the lattice parameters A and C, and the set coordinate of your structure. Okay, so having done that, of course the user wants to change the crystal structure and the data set within such a refinement macro set. Okay, for doing that you go into the cell folder. This contains just usually one word side cell, which looks like this. Pretty simple. Actually in the macro it's typed manually into the macro. And we want to change that now to the kaolinite structure, for example. So you have to put in your cell file into this folder. You have to create that case manually or from a zip file. Then you have to change your data set. So in our case this was the original data set, the PD32 whatever. Now we want to change it to another data file. So an other data set, which is just a copy of that data file. So it's an XY file with the data pretty much, and here are the uncertainties of X and Y. Okay, what else is interesting? So you don't have to change anything in those folders. They are partly empty. So the plot folder, for example, contains the result CIF file. So here you have a plot of the structure you calculated a few minutes ago. So this is a sphere of zinc selenide, and yeah, these files are partly empty. So what you necessarily need to do now, after you have modified your cell and your data set, you have to change that in the actual macros. You usually do that in the global macro. The global macro contains the data file, the data directory and so on, and here you have to put in your new data file name. So instead of the PD file, change it to other data file .dat. The second thing you need to do is to change your structure. The structure is standing in the zinc selenide macro here. Again, this is the zinc selenide, so it's manually written into this macro, so you can also read that from the cell file, which is done here. So you put in a read, read the structure from the kaolinite cell file, and here have added a few new lattice constants that we run actually a reasonable kaolinite structure, because everything apart from these lines, so for example in the make layers macros, they are kind of focused just on the zinc selenide structure. So I added another parameter here that it runs smoothly, because we haven't fine-tuned, for example, the layer distances of our new structure. You have to do that, but for just a quick structure change, it's completely sufficient to just read another structure into this Discus zinc selenide macro. Okay, having done that and having saved that, you can now rerun the refine macro with the second structure and another data set. So if you do that, everything should work. When we look into the plot macro, so again the result.cif file, if you just want to open it with any program, you see that the structure has changed. So from zinc selenide we switched to kaolinite. Again, the distances are not correct probably, but we changed parts of the structure, and new atom type, silicon and so on are added to the structure. So this works quite well. However, we expect now a really bad result for the fit, because of course this structure shouldn't fit the data set of the zinc selenide. And for looking at that, we can just open another Discus suite, because the other one is still running. Oh, it's finished now. Okay, so we can do it here. So we go to qplot. We are still in this folder, and we can do the k-single dot macro. Bam! You see the R value is at 1.4. So when we look at the data and the fit, we can see that the fit doesn't match the data at all. So if you want to plot that, see it's totally off. Of course, that's what expected. However, when we would run the whole refinement with the correct structure, which is the zinc selenide in this case, we look at that, reach an R value of 18.8%, and this should look like, this should look like this. Not. So if you do a scale, you see that the peaks are well fitted in general, and you can do SR qplot macros like the compare to see how your fit evolved over time. So the R value is declining. Also, other parameters like the lattice constants, well, parameters are refined the same way. So the first thing you can do is you can look at the diff of best macro, which contains the correct, or well, not correct, but the refinement parameters after, in this case, 999 generations, and you can actually run the diff of best macro. Then it calculates once more with these parameters through the refinement macros, and then you obtain in temp in the calc file 9999, for example, one of the calc files, your final structure. You can manually change that, of course, when you change the diff of best macro and the parameters in there. Of course, doing that on a single core takes a long time, so usually we do a parallel calculation to run those macros very fast. For example, on a desktop, well, you put it parallel 3 or whatever, how many cores you have you want to use, and then you can do the refinement or the refinement continue, and then it calculates just, yeah, you just see the loops running through your open window. Okay, yeah, that's pretty much it. Now I'm going to show you a few rules to remember, tips and tricks. To do that, in a future video we probably look at some advanced changes in structures and what we actually can really do with such an impressive and flexible tool like Discus. Thanks for listening.